Dear students, welcome back. This is section 4.5 that we will now discuss, where we will again discuss an important price process in financial mathematics. In detail, we will look at the price of a financial option, and that is given the name Black-Scholes-Merton equation. So we will reach the Black-Scholes-Merton equation to get to the price of an option. Recall my first lecture in which I discussed what an option was. I will briefly come back to that here. And the option price in this form has been developed in the 1972, 1973 approximately by Black and Scholes simultaneously with Robert Merton. And it has become a very fundamental equation in option pricing. It brought Scholes and Merton the Nobel Prize in 1997, and Fisher-Black passed away in 1995 already. So let's look at the basics to get to this option pricing equation. We start with the value of a portfolio at time t, and we call that xt. Xt is the value of a portfolio, and that portfolio consists of an investment in stocks and an investment in money part. And that money part is gaining a constant interest rate per unit of time, and we denote that by small r. The investment in the money market you can see as an investment, for example, in bonds. In Dutch, that is called obligaties. Bonds may give you a constant interest rate per unit time, and the other part of the portfolio is the more risky part. That is where a trader invests in the stock market. Why do we start with such a portfolio? Well, we will later see that this portfolio forms the basis for the seller of the option, the writer of the option. But that's for later worry. For now, we will first look at the dynamics of this portfolio xt. The basis for the price of the stock is the geometric Brownian motion, which we have just discussed, GBM, and the corresponding SDE was given like this. dSt is alpha st dt plus sigma st dwt. We have seen that before. It's connected to the Ito process, and we know the solution to this. You remember the solution from the previous lecture. St is equal to S0 e to the power alpha minus 1/2 sigma square t plus sigma wt. That is the price process that we will be using. That is the fundament of our model. When the stock would not develop exactly as we write it down here, of course, the option valuation model would also not be valid. Remember, we are just dealing with a mathematical model. This is just a mathematical model for the development of the stock price process. Time now is t0, and st0 we can read in the newspaper or online. And this is like the development of the stock price in the future, with this GBM, geometric Brownian motion development, with a specific growth rate and a specific uncertainty in the market, in the future market. It is based on historical findings, but it is again used for future development. It's not like a physical model where everything is known more or less, and we know the gravity, etc. No, this is partly based on human behavior, and therefore remember, it's always just a model. Well, with this we can make our portfolio X. It looks as follows. Portfolio X at time t, we invest an amount delta t in the stock with price st. So part of our portfolio delta t st is in the stocks, and the remaining part x minus delta t st, that is invested in the money market. So that is invested in these bonds or in the bank account. That is the part which gains a constant interest rate R per unit time, small r. So our portfolio is composed of two parts, delta t st, and the remaining part xt minus delta t st. And for those, we want to look at the change in portfolio. So the interest is the change in portfolio per unit time, dxt. dxt, well, remember we have delta stocks. So dxt is then connected to delta t dst. dxt is connected to delta t dst, the change in stock price for our delta stocks, and the remaining part x minus delta t st, that is an amount which we invested in the money market. So that grows with interest rate. Again, remember my first lecture, xt minus delta t st, that will grow with the interest rate and the period of time. So that is multiplied by r dt. These are the dynamics of our portfolio, and we can rewrite that, of course. That is as an Ito process. Always remember that it's very convenient to work with the differential form, but behind that is the integral form, the Ito process. Xt is equal to x0 plus the integral from 0 to t, delta u dsu plus the integral from 0 to t, xu minus delta u su times r times du. Now, for the dynamics of S, and ds we call the dynamics of S. For the dynamics of S, we know the geometric Brownian motion, and we can substitute them here, and we will do that in the next line. So here, dxt is delta times, and here are the dynamics of S, alpha st dt plus sigma st dwt. That is substituted here. And the other parts are x r dt, r x dt, minus r delta t st dt. These are the dynamics written out of our portfolio value x. Here we can combine the dt terms in one form, and the remaining part, so the three terms are combined, and the remaining part is the dw term. Combining these together gives us, in fact, r xt dt, which you find here, and this part here, and this part here, they can be glued together, being alpha minus r delta t st dt, and the remaining part is the dw part, sigma delta t st dwt. So here we have collected the dt terms and the dw term, and we see a risky part, that is the part there where S is involved, a part in the money market, that is this part, and that grows with interest rate R. And we typically also say that alpha minus R, that is something like a risk premium. Yeah, the growth rate of the stock, alpha, we typically say that is larger than R, putting money on a bank account. Otherwise, if that were the same, why would you invest in stocks? So alpha minus R is something like the risk premium. Sigma is the volatility, the uncertainty in the stock price. And these portfolio dynamics are consisting of three parts: a part which is growing with the money market, and a risky part. So we have the dynamics of X. Now, often in finance, we are not so much interested in the value at time t, not so much. We basically would like to know the value at time 0. And in order to get to the value at time 0, we use discounting. And we discount with R. And discounted processes represent the value of the, for example, the stock price ST at time 0. So we discount the price, that is e to the power minus RT ST. We are more interested in this discounted price process, and also in the discounted portfolio process. So also the portfolio, we discount back to time t. And that exponential e to the power minus rt, I have mentioned that in my very first lecture, right? That discounting, what is the value at time 0 if the value is at time t, if the value is x of t, that is e to the power minus rt times xt. The discounted processes. Well, how do we get to the discounted processes? That is, again, the Ito-Dublin formula. Which function f would we take for the Ito-Dublin formula? That would be something like e to the power minus rt times small x. And small x would be s if we look for the discounted price process, and small x would be capital XT if we look for the discounted portfolio process. Well, essentially what I just mentioned is in this line, right? We look for the SDE for the discounted price process and also for the SDE for the discounted portfolio process by means of the Ito-Dublin formula, and the f here, depending on t and x, is equal to e to the power minus rt times x. This is a fine function. The derivatives exist. The derivatives with respect to time, the first derivative, and it's continuous. And the first derivative with respect to x exists, and the second one as well, but that is equal to 0, of course. So df dt for this one, minus r e to the power minus rt times x is equal to minus r times the f itself. df dx, well, x is here just as x to the power 1. So that cancels out here for the first derivative. That is e to the power minus rt. There's no x anymore appearing here, so the second derivative is equal to 0. With the second derivative equal to 0, we will also not list that term in our Ito-Dublin formula. So in this case, in this specific case, where the second derivative is equal to 0, the dynamics d e to the power minus rt st, the change in the discounted price process, is by definition now df tst, and we write it as df dt plus df dx ds plus 0, right? To be complete, we need the second derivative term as well. We have all the forms, and we can substitute those. We see that one over here. We see this one over here. For ds, we have an expression. So let's substitute all these parts. Minus r e to the power minus rt, and for x we substitute st here times dt, and the part which relates to the first derivative with respect to x, where x is s in this case, is e to the power minus rt, and then we write out the dynamics of s immediately, being alpha s dt plus sigma s dwt. Again, here we can collect the dt terms, this one, and the remaining part dw. And doing that gives us finally alpha minus r e to the power minus rt st dt plus sigma e to the power minus rt st dwt. So these are the dynamics of e to the power minus rt st, the dynamics of our discounted price process. We can do the same for x, for xt, and again there the second derivative cancels out. So in this case means the second derivative doesn't appear here, and we can write the change in discounted portfolio process d e to the power minus rt xt being equal to the first derivative with respect to t minus r e to the power minus rt xt, in this case dt, plus the first derivative with respect to x e to the power minus RT dxt. Well, dxt we have just derived on the previous slide. Let's look at it again. Dxt was here, being that Rx dt plus alpha minus R delta t st dt plus sigma delta t st dwt. So we will substitute that for the dynamics of x for dx in the next slide. So doing that here gives us, the first term is just copied, minus R e to the power minus RT xt dt, plus the discount term e to the power minus RT, and then we substitute Rx t dt plus alpha minus R delta t st dt plus sigma delta t st dwt. Again, collecting the dx terms, the dw terms and the dt terms, we see that this one cancels out, this one and this one, they cancel out. And what remains is the discounted alpha minus R term here, dt, and the dw term. So what remains is e to the power minus RT, alpha minus R delta t st dt, plus e to the power minus RT sigma delta t st dwt. So we have found with the Ito Dublin formula, formulas for the dynamics of the discounted price process and the discounted portfolio process. And we have collected the DT terms and the DW terms here. So that's all nice. Let's continue with this exercise. So what we want to do now is we look a bit more carefully back at these two price processes. Here, what we see here is they are very similar, right? The discounting term is there, alpha minus RS is there, only the delta is different here in the discounted dynamics of the discounted portfolio process. We see delta appear here and we see delta appear here. For the rest, they are the same. So looking carefully, we see that again repeated the change in the discounted stock price process being written out like this, e to the power minus RT alpha minus RST dt plus e to the power minus RT sigma ST dwt. We see that the change in portfolio process is in fact delta times the change in price process. So the change in the discounted portfolio depends only on the change in the discounted stock price. That is an important notion to see, an important item to see. Now, what we'd like to do is we would like to evaluate a call option value. And in this part, I would like to repeat what I've done in my first lecture. Again, remember my time axis, T, running here, my stock axis, S, running here. Here is S0 somewhere. We have our K here. And remember that we had the call at final time. So at final time, we said the call is the maximum of ST minus K and 0. And we also write that as ST minus K plus. How was this again? Well, we had the following. We had we are now at time T0, right? This is T0. We are here at time capital T. And we have a model for the price process. Yeah, we have a model and it could go this way, it could go this way, it could go any way like this. But it could also go similarly, it could go this way, right? It could go this way. We have not yet a clear idea how this goes. What we know is that we model S T by geometric Brownian motion. We had an alpha for the growth rate, for the drift. We have a sigma for the volatility. So we have some notion where it may land. But again, remember that for all these final processes ST here, we would be able to buy the stock for K and immediately sell it in the market for ST. So we would make a profit ST minus K at final time. And for all these processes, we would be able to buy the stock for K, but it is cheaper to buy it in the market for ST. And then we would not exercise our option. So our option would expire valueless, so it would not be exercised, so it has no value anymore. And then that is essentially the zero here. The value of the option is in the payoff being the maximum of ST minus K and 0. And we write it like this. And then again, what we want to achieve today is what is the value of the option at time 0 and stock price 0, right? That is what we would like to know. Now, don't forget who is gonna set this price. That is the person who sells the option to the holder. So we have the writer or the trader, and we have the holder of the option. And the one who sells the option asks a price, right? Asks C0 S0 from the holder. Then the holder buys the option, pays this amount to the writer, and the writer uses this amount to compensate for all the risk, to be able to receive K and give out the stock at some value ST. Right? The writer determines this price of the option on the fact that there's no risk at final time. The writer, in other words, the trader, buys a portfolio at time 0, a portfolio of stocks and cash, exactly our portfolio X, buys the portfolio consisting of delta stocks and the remaining part in money in such a way that at final time, whatever happens, there is no gain nor losses. So the value of the option is basically the cost of the portfolio, the cost of maintaining the portfolio in such a way that at the end, obligations can be maintained and satisfied. I hope that's a little bit clear. So what we'd like to do now is we would like to evaluate that call option value. Recall at final time we know it. We know the payoff, ST minus K plus, the maximum of ST minus K and 0. K is the strike price agreed upon at time 0. And the payoff depends only on the price at final time. There are many, many other options, American options, Asian options, many other constructions. They may not only depend on the price at final time, but this European option depends only on the value of the stock at the final time. So recalling, this call option gives the buyer of the option the right, but not the obligation to buy the stock at time T for a price K. That is the value at final time. The buyer, so the holder, the buyer is the holder, remember, the buyer of this option has to pay for this right. Yeah, he has to pay, or she has to pay to buy the option. An option is a derivative. You get an extra opportunity, namely to buy stock for K at final time. That contract costs money. To get that extra right costs you something. Now let small c, depending on T and X, let that be the price or the value of the European call option at time T. And then ST is equal to X. So the value of the option at time T at the value, stock value ST. We would like to determine a formula for XT and X. So for any time T, we would like to know the value of the call option. Particularly, we would like to know it at time T0. Yeah, we would like to determine the option value at any time between 0 and capital T. We know it at final time, of course, that is our payoff. But we particularly would like to know it at time 0, but preferably we would like to know it at any time. We would like to determine an SDE for the process C. And we will later see that in fact, it will not be an SDE, but we will get to a partial differential equation, a PDE. So we consider our function C of T and X. It has continuous first and second partial derivatives, and we can use the Ito-Duplin's formula. Yeah. So the change in call option value at the time T ST, that is dC dt dt plus dC dx ds plus 1/2 the second derivative of C with respect to X times ds ds. ds we know, that is our price process. These are the price process dynamics. And dst we also know, right? That is connected to our quadratic variation. So let's substitute everything that we know. dC dt remains dt. Yeah. Then here for ds we substitute alpha s dt plus sigma s dwt. So we have dc dx or dc ds if you wish, right? It's s. dc ds times alpha s dt plus sigma s dwt. And the last term related to the second derivative, there we substitute for here, we substitute the quadratic variation. So that was, remember in differential notation, sigma square s square dt. So plus 1/2 the second derivative of C with respect to X at time T and ST, sigma square s square dt. So this is a representation of the dynamics of C, the dynamics of the call option price. Again, what we can do is we can collect the dt terms and the dw terms. So let's do that. We see a dt term here, dc dt, that is here appearing. We see here alpha s dc dx dt, that is copied over here. And here we also have a dt term, 1/2 the second derivative of C with respect to X times sigma square s square, that is the one here. And the last part that remains is the dw term, so that's the uncertainty in the option price if you wish, that is sigma st dwt, and that we see over here. So we have a form for the dynamics of the call option value. The dynamics of the call option value. What shall we do with that? What shall we do with those dynamics? Well, the first thing we do is we would like again to look at it by means of discounting. We want to look at it at time 0. So we consider the discounted process, e to the power minus RT times C. So we use Ito-Duplin's formula. We apply again it to the function f, which depends on t and x being e to the power minus RT times x, where for x we now think of the call option value. df dt, again, minus r e to the power minus RT times x. df dx is minus RT e to the power minus RT, and the second derivative being equal to 0. Let's do that. The change in the discounted option value, d e to the power minus RT CT as t, that is then minus R e to the power minus RT C of T and ST dt related to the first derivative. Here we see the first derivative appear. Here we have e to the power minus RT dC of T and ST, and dC of T and ST we have just computed in the previous slide. Here you see it, dC of T and ST. So this we can substitute. dC dt, dC dx, second derivative, a dt term, and a dC dx dw term. So let's substitute that. Here, the first term remains. That is the first term, minus R e to the power minus RT C dt. And then the discount term e to the power minus RT is outside the brackets. And what is inside is a dt term representing dC dt plus alpha S dC dx, dC ds, that is, of course, plus 1/2 the second derivative of C with respect to S, sigma square S square dt, plus the remaining term discounting e to the power minus RT dC dx times sigma st dwt. So we also have the dynamics. We have the dynamics here, the SDE for the discounted call option. Now, how do we then find the fair value of the option? So what is the fair value is what is the money needed for the writer to get to be able to sell the option and to have essentially no risk, to have all the money needed during the time from 0 to capital T, to have all the money needed to be able to obey the obligations. So we want to have a fair option value C at time 0 and S0. That means that the option seller should be able to start with an amount x0, so an amount in the portfolio S x0, and that should be equal to the value of the option at time 0, at S0, yeah, the value of the option at time 0 at S0. This is one of the things that we would require. The value of the portfolio that is then in the hands of the option seller should be equal to the value of the option itself. That would be a fair value. Of course, a trader may ask a bit more than this because the trader wants to make some money, but this is the definition of a fair value. And then the option seller would build a portfolio process, XT, for the time running from 0 to capital T, so that for each time T in the future, it holds that the value of the portfolio at time T is equal to the option value at time T. That is the aim of the option seller, particularly at final time capital T, the value of the portfolio should be equal to the value of the option, meaning that if the option would be exercised, the value would be present in the portfolio of the option seller. And that is called no arbitrage. There's no arbitrage, so this would mean that at any point in time, the option seller is able to satisfy the duties that he may have. And this portfolio X consisting of stocks and bonds, this portfolio is called a hedging portfolio or an insurance portfolio. Hedging is like a form of insuring. So again, remember, the writer is not selling it and do nothing and hope for the best. No, the writer is immediately when the money, the premium, the option premium is received, the money is immediately invested in stocks and bonds in such a way that during the whole time process of the option, the whole time process, the value of the portfolio is equal to the value of the option, particularly at final time. So we want, moreover, what we really want is that the discounted portfolio process is equal to the discounted option value, call option value. And the same for a put option, right? We can also do this for the put option. We do not explicitly see call or put appearing in this. It's just a notion that there is a portfolio consisting of stocks and bonds, and this portfolio, the discounted value, should be equal to the discounted value of the option. In this case, the call option at time t. So we have these processes, we can equate them. So particularly, we would like to have the change in the discounted portfolio process being equal to the change in the discounted option value process. D e to the power minus RT xt should be equal to D e to the power minus RT ct. So if we would like to have this, we have a closed form expression, or we have an expression for these dynamics, and we have an expression for these dynamics. And recall that the dynamics of the discounted portfolio process consisted of a dt term and a dw term, and the same was true for the discounted option value, a term with dt and a term with dw. So if we want these to be the same, that means we would need to equate the dt terms and we would need to equate the dw terms. Now, for the dw terms, this is the most easy one. Recall that we only had one term. In both dynamics, we had one term. So it's easiest to look at those. Here, we repeat the change of the discounted portfolio term. And here we see the dw term appearing, sigma e to the power minus RT, delta, the number of stocks, delta stocks, time-dependent number of stocks, times the stock price, ST dw. And that should be equal to the discounted option value, and we have seen that. And let's go back there to, here we have that. To see what that is, e to the power minus RT, dc dx, times sigma times st dwt. So we see some of the terms already reappear. E to the power minus RT is in both expressions. Sigma and s is there. Here is dc dx or dc ds in this case. And the other part we had delta. Yeah, so here we had delta. The delta here. That's the only difference in the dw terms. So they should be equal in order to force this equality. That's on the next slide. So we want to equate the dw terms in equation 3. Equation 3 is the dynamics of the discounted portfolio equal to the dynamics of the discounted call option value. And basically that means if we equate the dw terms, that e to the power minus RT dc ds times sigma times s should be equal to sigma e to the power minus RT delta s delta t times st. And equating these means that the CDS should be equal to delta. So dCDS should be equal to delta. That is one condition that we require. One condition that we require in order for this equality to hold. And mind you, this tells us that the first derivative of the call option value at any time t and st should be equal to the number of stocks in that portfolio. This is basically what this implies. Now we also want to equate the dt terms, so we list them here. These are the dt terms for the discounted option value, e to the power minus rt times minus rc plus dc dt plus alpha s dcds plus 1/2 the second derivative of c with respect to s squared times sigma squared times s squared dt. And that should be equal to the dt term in the discounted portfolio value. And that was equal to alpha minus r e to the power minus rt times delta t st dt. You can see that over here, right? You can see that over here. This is the dt term here, and that is equating the dt terms tells us that this should hold. Now some terms now cancel out. You see, first of all, the discounting term need not be there. The dt term, of course, need not be there. What else do we see? We see some term, of course, remember that this is basically this dc dx, right? This is now cx because of this here. So if we substitute that, dc dx, we have minus r here on the right-hand side, and we have alpha here, alpha s cx here, and we have alpha s cx here. So the alpha term also cancel out. And what remains is a very convenient form. So what remains is a very convenient form, being the so-called Black-Scholes equation. RC is equal to dc dt plus rs dc ds plus 1/2 the second derivative of c with respect to s times sigma square s squared. So dc dt plus rs dc ds plus 1/2 sigma square s squared, the second derivative of c with respect to s squared, minus rc is equal to 0. And that is the Black-Scholes equation. And you see that because we have taken this, we forced this equality, that the number of stocks in the portfolio should be equal to dCDS. Because of that, the randomness has canceled out, the dw terms have disappeared, and what remains is a partial differential equation. An equation with time t, partial derivatives with respect to time, and partial derivatives with respect to s. And this is the Black-Scholes-Merton partial differential equation. It's a parabolic partial differential equation. It has a first and second derivative with respect to s. It has a zeroth derivative, and it has dc dt. Well, we will solve this equation in chapter 5, but now at least I would like to show you the solution. And again, we wish to solve the PDE, we wish to solve the partial differential equation, and the only thing we know is that at final time, we know the value. It's the value of the call option, the maximum of st minus k and 0. And essentially, if you think about it, that's the only place where explicitly the call option features appear. It's only in the final condition where we use the fact that we're dealing with a call option. So you can imagine that exactly the same equation appears if we would look at the put option, but for the put option, we would have a different final condition being K minus ST plus, yeah, the maximum of K minus ST and 0. That would be the equivalent form for the put option. Now here, so the solution is given in exercise 4.9, and that will be discussed later this week. But the derivation will be done in more detail in chapter 5. And here we will just give the answer, and you can check yourself that it satisfies the Black-Scholes-Merton equation. You can do that by, well, if we have a solution, it should satisfy the equation. So the solution, which would be a function c depending on t and st, it will have some expression. Well, that expression, for that we can take the first derivative with respect to t, the first derivative with respect to s, second derivative with respect to s. We substitute all these expressions in this equation, and it should, and here it should also be substituted, and then it should be equal 0, right? Only then it is a solution to this equation. Now, the solution that we find at any time t for x, where x is of course st. So for x we can substitute st. The solution to the call option at any time t with as argument x st is given as follows. It's x times the normal distribution which with as argument a term d plus, with the two arguments in itself, t minus t and x, minus k times e to the power minus rt minus t, times again the normal distribution with as argument d minus, with inner arguments t minus t and x. So that is the solution. Of course, this is the standard normal, and the argument here is always the upper bound of the integral. We will see that a slide from now. So we have these d plus and this d minus terms. These are functions. And the first argument, let's call it tau. T minus t, let's call it tau. Then this d plus and d minus, they are written as follows. 1 over sigma times the square root of tau times the log of x over k plus r plus or minus sigma square over 2 times tau. It's the plus term when we're dealing with d plus, and it's the minus term when we're dealing with d minus here. Here's the d plus, and here's the d minus. And recall, for the standard normal distribution function, we have n of y with argument y. It's 1 over the square root of 2 pi. The integral from minus infinity to that y, to that argument, which is then d plus in this case and d minus in this case, times e to the power minus 1/2 u squared du. This is the solution. It looks a little bit involved because of this normal distribution, but it is a closed form solution, right? And with this closed form solution, we essentially we have the value of the option at any time, at any s value prior to maturity time capital T. Particularly, we have the value with this C0, S0, right? We can substitute T0, and then of course, capital T minus T would be capital T, and S0 we can substitute for X, and in that case, we get an expression which represents the value of the option. At the same time, that represents the value of the portfolio. And so that is the value of the option, and with that amount of money, we can buy delta stocks and invest the remaining part in a money savings account or in bonds in such a way that by the end of the contract, we would have enough money or enough stocks to satisfy, to pay out if the holder decides to exercise. When the holder decides to exercise, the writer would receive K and would have to give away the stock. And with this amount and with delta stocks all the time, changing delta. Delta, remember, was a time-dependent function. With changing the number of stocks in the portfolio time step by time step, we make sure that for this money C, we will have the value ST in the portfolio of the writer when the writer needs to sell it. And when the stock is lower than K, then the writer need not do anything. Then there will not be any stock left in the portfolio. So C0 S0 would represent the money, the fair value of the option, the money needed to define that portfolio and to change that portfolio time step by time step to be able to hold the obligations of the writer that may occur in the future. Again, it is a model. There are model situations. There are model assumptions. No transaction costs for changing the delta, for example. No transaction costs for buying and selling stocks in the portfolio. There's no dividend payment. There is, well, delta can be any number. It can be a negative number, that means short selling. It can be a positive number. It need not be an integer. So there are some assumptions here. And the most important assumption is that S of t is, of course, a geometric Brownian motion. The assumption that the stock value develops like a geometric Brownian motion. Under that assumption, this would be the value of the European call option. And that concludes 4.5. I thank you for your attention. Sometimes we write this as a function, just a function in the computer, Black-Scholes-Merton. It has as input tau, t minus t, x, st, the strike value, the interest rate, the value, and the value for the volatility. And with that, this is computed, and then we get as output the value of the option. That concludes today's lecture. Thank you for your attention.